Okay, here's a video for section 12.1. In this section, we're doing the goodness of fit test. For this test, they're going to give you a list of observed values, and in some cases, they'll give you a list of expected as well. As you'll see in the next problem, sometimes they give you a list of probabilities or percentages, decimals, and you're going to have to convert that into this list of expected. So I'll show you that in just a second. But for this problem, I put the two lists into list 1 and list 2. So 19, 21, 21, 19, that's these. And all 20s for the second list, observed and expected. All right, the test we're doing here is the goodness of fit test. So if you go over to test, go almost all the way down to goodness of fit test. Not this one, not the chi-square test. You want the GOF test, goodness of fit. They'll ask you for the two lists. So I have mine into list 1 and list 2. My degrees of freedom, the number of categories that you have. So we have 4 categories here. So take 1 away from that, we get 3 as the number of categories. Calculate. We get a test statistic of 0.2. Notice this p-value is extremely large. It's a very, very rare p-value. Degrees of freedom are 3. I talked about that, 1 less than the number of categories you have. Here's the tricky part for this one is this critical value. To look up this critical value, you need the table. They did not give you the table in this problem. They should have, but they give it to you in the next problem. There's no way to look up this critical value on the calculator. The TI-84 doesn't have the chi-square test inside of it, so you need to go and look at the distribution table. So on number 3, it actually does give you the table, which is ironic because you don't need it for this problem. So here's what we're looking for. For the problem that we're working on, number 2, we have an alpha of 0.05, I'll show you that in a second, and a degrees of freedom of 3. So you're gonna go down to 3, you're gonna go all the way over to 0.05, and this area is 7.815. That's your critical value. This is the area to the right of the critical value. These goodness of fit tests are always right-tailed tests 100% of the time. So we know that whatever area they give you, that's going to be the area in the right tail. I want to show you this as a picture as well. So keep note of that 7.815. So back on this problem, that's our critical value right there, 7.815. I want to show you a picture for this. This is what the chi-square distribution looks like. It's bigger on the right-hand side, on the left-hand side, and it has a long right-hand tail. So this critical region is the area to the right of the critical value. In this case, go back to red, we have a critical value of 7.815. That would be this line right here. That's the demarcation of the critical region. Now, where your test statistic ends up lying is going to tell you whether you reject or fail to reject the null hypothesis. If your test statistic ends up being here, then you're going to say do not reject. If your test statistic ends up being here in the critical region, then you're going to reject the null hypothesis. So in this case, for our problem, we have a test statistic, a very small test statistic of 0.2. So that would actually be way over here, which is, hang on, redraw that. Why that happens sometimes. So our test statistic would actually be somewhere like over here at 0.2. That's well outside of the critical region. So our answer in this case would be we would say do not reject the null hypothesis. And here's the reason. So it's asking, should we reject the null hypothesis? We say no, because the chi-naught squared, that's the test statistic, is less than or equal to the critical value. This number here is the critical value. So the test statistic is less than the critical value, so we would not reject the null hypothesis. Okay, I'll show you that again for the next problem as well. I can compare that also. So let's look at this one. Okay, they give us a list of data values. So they give us these frequencies. That's our list 1. So I kind of have these in the calculator. I'm going to cheat a little bit. I put them in the list 4 and okay, so that's all the these frequencies here. Now here's what I recommend. Let me clear these out for list 2. In list 3, I'm going to put all these probabilities here. So all these percentages, 0.13, 0.14, I'm putting them into list 3. These are not your expected frequencies. These are just the percentages that will give you your expected frequencies. So I would put those into a list, and then in list 2, you're going to take those numbers. So I'm going to multiply list 3 times the total of all of the numbers. So I'm adding up 60, 64, 54, 59, 97, 65. That gives me my sample size, which I added those up and got 399. So if you multiply that times all these percentage values, then you'd get your list of expected frequencies. So that's what I'm going to put here as my expected count, 51.87, 55.86. It's all these numbers that the calculator gave you. The null hypothesis for all of these goodness of fit tests, it's always the distribution is the same as what was stated, and the alternative says the distribution is not the same as what was stated. So that part's actually pretty easy for this chapter. The test statistic. All right, so now we have our list 1 and list 2. We have our observed values and our expected values. So the test I'm going to do, I'm going to do this chi-squared goodness of fit test, list 1 and list 2. My degrees of freedom now, there's 6 categories, so my degrees of freedom would be 5. Hit calculate. I get a test statistic of 20.388. I get a very small p-value. P-value is 0.001, so that is less than 0.01. They give you a lot of options for this choice here. This is the only one that worked. So because we have a very small p-value, we would say reject the null hypothesis, and we would say there is sufficient evidence. Rejecting and is sufficient evidence always go together. Remember that. Okay. Let me show you the picture for this one. So we have I want to show you these two. A test statistic of 20.388. Let me write that down. And we have an alpha here of 0.05. Let me go look up the critical value. So here's our table of critical values. We have a degrees of freedom is 5, and our alpha is 0.05. So we have a critical value right here of 11.070. Okay, so let's go back to our picture then. And over here. So now we have this new critical value. So I'm going to do this as red. Our critical value would be 11.070. So 11.070. That's our critical value. Our test statistic is 20. The chi-square distribution, it starts at 0 and it goes positive to the right. So if this is 0, then maybe about here's 1, here's 2, here's 3, here's 4. We get to here, we're at 11. So 20.388 is, I don't know, doesn't really matter, but it's somewhere over here on the right-hand side. Let's call it right there because we already have a line here. So let's say that that's about 20.388. So because our test statistic is inside of the critical region, we would say reject the null hypothesis. But if the test statistic is inside that red critical region, then we reject the null hypothesis. So back on our problem, you can use the p-value to make that assumption as well. So we would reject the null hypothesis. There is sufficient evidence. Okay, hopefully that makes sense and helps you out with some of that homework. Most of those other homework problems should be very similar to that. So keep up the hard work. We're almost done.